It's on now, apparently. Awesome. Yeah, I want to thank Steve for slotting me in first because I have to get home for a birthday tomorrow. So thank you very much. So welcome, everyone. I'm really happy to kind of open DeclMed here, talking about our work in molecular programming and developing abstractions for it, rooted in reactive functional programming. And so is anyone here a doctor? Crap. Okay, I'm going to do my best. So I'm a programming languages person by trade, so please forgive me for everything that's going to happen here, right? So just to kind of motivate this idea about molecular programming, let's just kind of consider a person who is undergoing some sort of ailment. Maybe some sort of disease like cancer or something like that, or maybe they just have some need for some drug that needs to be administered at either regular intervals or in a very specific area, right, or in a very targeted fashion, right? How might we approach this problem? One idea, we might use traditional electronics to be able to do this, right? Perform invasive surgery, embed a microcontroller that can sort of regulate drugs, like a pacemaker, for example, or something like that. This, of course, we know how to work with these devices, right? They pervade everyday life, and so why not inside of us, right? But of course, there's obvious downsides to this, right? They're invasive. You have to put them inside someone via surgery. Not cool, right? And also, as much as we care, like they're not actually very precise, right? Short of having very, very little tiny robots in there, right? A little regulator in your arm won't be able to sort of sense what's going on in the rest of your body, right? And so one innovation that's happening in this space is the development of nanorobots, right? And so here's an example of a nanorobot by Li Zhang and Wu from 2021. It's a little fish robot, and the idea behind it is that it's a little fish shape, 25 nanometers or so in size, with a little mouth, and it stays closed. And it has a little drug payload inside of it. And so you can put this inside of someone's body, have it go inside the body, and they do this via magnet just to sort of as a proof of concept in sort of an artificial sort of blood system. Steer it to where it needs to deliver the drug. And in this particular case, I believe the pH concentration around kind of the area where the drug should be activated is higher. And so the mouth then opens up and then releases the drug in a very targeted, directed fashion, right? And so that's super great. Completely non-invasive. You just put little fishes inside of you. Fishes are natural, right? So that's fine. It's precise, right? We can directly deliver the drug to exactly the places they need. A very, for example, for cancer drugs, a very important property to have. But there's one question. Are they programmable, right? And so that's a simple example of, opening your mouth for, a pH imbalance, right? It's relatively simple, but maybe we want to have richer logic there. Right? Maybe if there's a certain presence of some molecules and not other molecules, or actually have some deep logic there. And so that leads to our question, well, how do we actually program these things, right? And so molecular programming is the idea that we can program at the nanoscale, right? Really, what do we mean by that? Is that we're programming not using sort of traditional electronics, but using the reactivity of molecular compounds instead, all right? And this has a whole bunch of applications. I like the precision medicine one the most. It speaks to me the most personally, but there's lots of other applications for nanofabrication, data archival, using molecules directly, and then cyber biological systems and tons of other stuff, right? And so the main problems in this space, the first, less germane, at least for me, because I don't understand any of this, is how do we actually use these different chemical compounds, right? And there's lots of different options out there. The one most prevalent, the one I'm most nominally familiar with, is DNA. But there's other ways that we can sort of get chemical effect or computational effects using chemicals. A little bit closer to home, right? What is actually possible with computation, right? Are we able to do Turing-complete computation, or are we stuck with subsets of computation that may or may not capture what we want? A little bit closer to home now. Getting closer now, right? How do we perform robust computation, right? And you can kind of imagine this substrate, just like the advent of like traditional electrical computation, right, was filled with issues around robustness. How do we actually get our circuits to be reliable and consistent, right? Same thing here. And then finally, really close to home, right? How do we actually do all this computation in a way that's reasonable for human beings to actually do, all right? And so that's going to be kind of our little foray today, is these abstractions. And so let's kind of dive into it. In this first part of the talk, I'm going to kind of introduce people to some of the basics of chemistry. Again, the average in this room probably is higher than me as far as knowing stuff, so I apologize for that. But just kind of giving some background, right? So reminder, high school chemistry, right? So chemical reactions look like this. Sulfur and dioxygen combine to, or dioxide combines into sulfur dioxide, right? And so this is, so if you don't remember how these reactions work, right? We have a collection of reactants on the left that when present together will combine to form a set of products, right? This is, of course, sulfur dioxide. This is kind of that smell you get when you burn matches, right? So that's all well and good on the chemical side, but more interesting, what is it computationally, right? And so let's think about that real quick. Sulfur and dioxide combine to form this compound, right? It doesn't seem like there's a computation happening there, but if we think about it a little bit, we have inputs on the left-hand side. We take sulfur and dioxide on the left, and then we produce something on the right-hand side. We just ask the question is, what do we actually produce? What is that? How can we computationally interpret that? Well, if we look at a graph of those reactants over time, right, the blue is the output in particular, we can see that over time, if we start with a given quantity of sulfur in red, that was a convenient color, dioxide in green, right, the blue, the output, converges to the original value of the green quantity, right? So what are we actually computing there? It's the min of those two inputs, right? So intuitively, what's happening there, right? We are consuming the S's and O2s combine until there's none of one of those left. The one that runs out first is the minimum of the two values, represented by the sulfur dioxide, right? And so that's kind of a key insight here, right? And kind of, for me, the first time I saw this, I was like, oh crap, that's a completely different programming paradigm. This is bananas, right? It's interesting that we can get computational effects like this. And so let's look at another example. This one's a little bit more complicated. I want to walk you through it real quick. And so what are we doing here with these four reactions, right? And note that I haven't listed chemicals there, right? So they're just kind of abstract for now, right? So that first first two equations on the left are doing two things, right? First, we're turning the x1s into a1s and then x2s into a2s. And then along the way, we're producing y's, okay? Those y's will then be the sum of the x1s and x2s. Next, we perform a min computation. You might recognize that from the previous slide, right? That's performing a min of A1s and A2s, right? And then the final thing is effectively doing a subtraction. We're going to be combining Y's and B's and just annihilating them, effectively performing the computation sum minus min. And so what are we getting overall? We're getting the max computation. So you can kind of see here how the Y converges to the initial value of x1, which was 500 millimoles over there, right? And so, yeah. So we're able to perform these sorts of computations. What we just saw is an example of kind of our underlying model for computation, the abstract chemical reaction network, right? And chemical reaction networks form kind of a basic assembly language for molecular computation, right? It turns out they're Turing universal, both in their deterministic and non-deterministic variants, which I'll talk about briefly later on. So we have kind of this very rich potential for computation using this model, right? Note that these chemicals are abstract, and you might notice some issues with this if you invoke chemistry. One, what chemicals actually do that? Two, those aren't balanced equations at all, right? And so the good news is that we can sort of sidestep those issues. The first is that we can use DNA to manufacture molecules that react in those ways. This is where I'm completely out of my league, but techniques like DNA strand displacement allows us to be able to create molecules that exactly match a set of reactions we have in mind. And then also, there's fuel molecules there to sort of balance everything out. So, right? And so, yeah, that's kind of our model of computation. To give you kind of an example of something a little bit more detail, right? Here's an example of a recent work we just published in IEEE Allerton this year, verifying a particular computation in Isabelle. It's the hailstone function. So these sets of reactions compute the hailstone function from the Coalesced conjecture. And so less important to actually understand what the hell's going on, more to like maybe intimidate you, because it is kind of complicated and really motivates the need for language abstractions, right? But we can break this up into parts. theoretically those parts, right? And so just like with any programming problem, we have to break up our computation into smaller bite-sized chunks, right? Composition is the key to building up larger things. Even though this is a very simple computation, right, we still have to go through all that rigmarole, especially because we're working with such elementary substrates, chemical reactions, okay? And so in this particular case, composition is relatively straightforward, right? I was able to kind of break things up into these chunks, and if you believe me, in our proof, we actually go through all the pain of like proving that all the parts do what they do, and then in combination, they all do what they do, right? It seems like it's relatively straightforward, but because of how chemical reactions work, that's not always the case. Let me give you an example of this. So we saw min and max already, and those are the two reactions there. Suppose I want to compute something that is the composition of those two functions, the min of the max, just for argument's sake, right? A very natural idea to compose the two reactions is to simply just tie inputs and outputs together. And so in this new reaction that I built that computes the min of the maxes of x1 and x2 coupled with x3, right? All I've done is I've taken the max reaction, renamed the output y to z. I could have picked better names there, I apologize. And then that becomes the input to the min computation, right? The first four reactions are the max computation, the last one is the min computation. Pretty straightforward, all right? And so it's a valid CRN. That's a good thing, right? However, if we actually run this computation in simulation, we see that the y value that we get, which is the output in this case, it's not z, I apologize for that, is definitely not the min of the max of x1, x2, and x3. It should have been, I believe it's the red line of, I think that's like 500 millimoles or something like that, right? But it's definitely a lot more. So what happened there, right? We actually have a race condition, unfortunately, right? Because note that in our computation, the min and max computations were both trying to chomp down on the intermediate Z molecule that we created to fuel the computation, right? And so in that respect, we can't actually just compose these naively. It doesn't work, right? It sucks. But guess what? Programming languages to the rescue finally, which is great, right? And so that's kind of where our work steps in. And so just to kind of give you a high-level idea, what are we trying to do here? We're trying to operate, obviously, at a higher level of abstraction. Programming in chemical reactions is definitely a no-go for any sort of real work. It's not good. And so our main idea here is to envision chemical reaction networks as sort of circuit-like programs, right? And you kind of have a sense that they sort of do operate kind of like circuits. I'll kind of show you an example in a second. In addition to that, we want to try to stay, how do I put this? It's kind of a design quality more than anything else, right? We want to capture kind of the nature of CRNs directly. We don't want to build too much runtime that loses that essential parallel continuous nature of the computation that's happening. And so luckily, programming language community has something for that. We have this idea of a continuous reactive programming paradigm. And so we're going to realize our CRNs as continuous reactive networks, right? And so the final thing is compositionality and correctness guarantees, something that the ICFB community loves, right? And so we're just going to use the word functional in the front, and all of a sudden everything is solved. This is great, right? And so that's kind of our shtick, is this idea that we're going to realize CRNs as functional reactive programs, right? There's been a lot of work here before, just for the record. I want to pay a lot of respect to kind of these past works. A pair of things from Microsoft, and our community knows Luca Cardelli. He's been working in this space quite a bit over the last couple of years. He just recently released this app, Kameka, for building CRNs as well. And there's also this CRN++ thing that is kind of like a more imperative assembly language for CRN programming. The problems with these things that we're trying to sidestep, right? They're either too low level. The first three there kind of operate on reactions directly, and then the last one really, to get that imperative feel, puts in timers and runtime support that we want to try to avoid. We want to try to program directly against kind of those reactions in a more natural way, rather than sort of essentially building a computer as we sort of understand it on top of kind of molecules. And so let's go ahead. I'm just going to briefly show you kind of an example to see what this looks like, and then we'll go into a little bit more detail for the remainder of the talk. And so let's look at how we might encode sign using our language reactimal. And so first fact, Thanks to the power of integration, we might realize that the way we might define sign in terms of itself is the double integration of sign is equal to the negation of sign, right? And so if we think of what that might look like as a circuit, it might look like this, right? We're going to perform the negation of two integrals and then loop that back on itself, all right? And that's going to be our definition for what sign is, all right? In Reactimal, it looks like the following Haskell program. Whoops, my bad. There's a transition there. Just to kind of show you there, right? Because this is a feedback loop that's just outputting a sine wave, we're going to ignore the input here. And it looks like that. And so in Reactimal, we write a Haskell program using, if you're familiar with Yampa, the key idea is that we're just kind of using the Yampa sort of style DSL for reactive programming. Sign is defined to be a loop over the negation of two integrations fed back on itself. That sign function, when run through Reactimal, produces that set of reactions there, which we'll look at a little bit in a bit, so don't worry about it too much. And then when simulated, produces what I hope is a sine wave. So it works kind of, at least in simulation. So that's kind of the idea behind Reactimal. And so Reactimal is a functional reactive molecular programming language written as an embedded domain-specific language in Haskell, although we'll be moving away from that in the near future for reasons I'll get at the end of the talk. In particular, our approach to functional reactive programming is inspired by Yampa using this arrowized approach, where we have a program is the combination of a bunch of primitive signals built up with combinators to allow us to build more complicated signals from simpler signals. Our key insight is a direct translation of kind of the signal language from FRP into the world of chemical reaction networks. It's pretty straightforward. A signal is a chemical reaction network. A signal in the FRP world is a time-varying value of type A. A CRN we can think of as a time-varying set of concentrations changing that represent a value of type A. And a signal function, the main sort of workhorse within the FRP setup as realized by Yampa, is a transformer over signals, allowing us to map one signal to another. That's simply just a CRN transformer for us, allowing us to transform one CRN into another. And so some other notes here. Reactimal works over specifically deterministic CRNs. There are actually two models of computation that happen there. We work over kind of the deterministic variant where we assume that there's enough molecules in the vat that they all mix with equal probability. And there are other models where we deal with situations where you don't have as many molecules in the vat, probabilistic models that are open for future investigation. The other thing too, and this is kind of the key thing that we employ, one of my collaborators developed this notion of an IOCRN that corresponds specifically to purity in sort of a programming context. Namely, an IOCRN is one where the chemical reaction network is catalytic in its inputs. And so what that means is that the inputs are not actually consumed, which corresponds to not mutating the inputs, which allows us to get compositionality roughly for free, which is nice. Okay. And so I'm going to kind of blow through this a little bit. I want to talk about data and then kind of talk about how the combinators and Reactimal work to close, right? And so data is kind of an interesting sort of just question. How do we represent data inside of a molecular program, right? Booleans are a good example. Our first shot at that might be to just have one molecular concentration represent one Boolean, right? And so let B be that molecule, and then we'll interpret it, its truthiness to be whether the concentration is greater than 0 or something like that. The problem, of course, is that concentrations can't be negative, concentrations can't be negative, and having absolutely nothing inside of the vat of a particular molecule is difficult to detect, right? Our reactions work in the presence of things, not in the absence of things. And so this is kind of a no-go for practical computation. Instead, what we choose is this dual rail representation where we have two molecules represent a Boolean, and the difference of them will tell us, whether one is greater than the other will tell us whether we have a true value or not. All right? And so we can play this game with kind of all of our other basic data types, at least numbers and numbers, really, right? So Booleans we represent as a dual represented pair of molecules. Real numbers are the same thing, where we take the difference because we can't have negative molecules, so it's hard to represent a negative value. This also has some nice properties with our correspondence with general analog computing. The unit value is nothing. Pairs actually just work out beautifully because all the molecules just sit in soup, and so you just pair things by just noting that these things are together, but you don't have to employ any actual physical structure behind them. We actually have a story around tagged pairs, i.e. ethers, where we actually entangle a signal in sort of this dynamic switching style, which is really neat. We don't have time to talk about that today, unfortunately. And so primitive CRNs in Reactimal are just reactions, and so an example of this is our NAND primitive. And so it's just this reaction that my collaborators developed, which allows us to encode the totality of Boolean logic within our language immediately. And so we do that, which is great. But I'll sort of kind of close just talking about what this looks like for the actual arrow combinators that we see in reactive programming. And it's pretty straightforward. So looking at our example of integrating twice and then composing those together, how do we do that? Well, we form a chemical reaction network with an input and output. And just focusing on each of these parts in turn, integrate 1 is, we have integrate 1 and integrate 0. And so we're going to compose them together using our forward application operator taken from functional reactive programming. Integrate 1 looks like that. So that chemical reaction is primitive in our language. It works with those initial conditions. And then integrate 0 is similar. And the difference between the 1 and 0, the 1 and 0 correspond to the integral, the constant of integration, just changes the initial value. All right? And so because these are catalytic in their inputs, composing them is straightforward, right? We're just going to patch the inputs and outputs together in the expected way, and everything just kind of works. All right? And that was kind of the main thing here, is that idea, when we work with input-output CRNs, just works across the entire board for the entire suite of combinators in Yampa. And so we have a direct translation for all of these sorts of combinators. So we just saw forward application, things like, for example, split. I think that's split. We can just duplicate the signal. That would be like A goes to A plus B or something like that, so that you create 2 copies of the molecule. When we have things working in parallel, because we're in a soup, they just work in parallel naturally. There's no need to do anything else. And since they're catalytic on inputs, we know that no reactions will be affecting other reactions and so forth. And then loop is implemented via backpatching on the CRN. And so yeah, that's kind of Reactimal in a nutshell. There's a lot of stuff there, a lot of technical detail, but I just want to give you a sense of it. We've shared this with sort of the molecular programming community, and then they saw the Haskell code and got scared, and I felt bad. So I want to show you all it, just kind of show you, especially in line with the first talk at ICFP. There's lots of cool stuff, lots of applications to functional programming out there, and we're still kind of in the thick of it. As I mentioned, it turns out Haskell as a DSL, we're not quite fully an arrowized language. If you're familiar with Haskell, specifically because we can't lift arbitrary computation into molecules, it turns out. Representing higher order functions, future area of research for sure, right? And so my plan is to sort of develop this into a separate language that chemists can use potentially to sort of explore the space. There's a lot of like meta-theoretic stuff that we still need to sort of prove about the language as well. I'm a type theorist. And so there's always a question of types. Very oddly enough, I started this conversation with my collaborator talking about how he verifies his chemical reaction networks, and he mentioned linear temporal logic. And then just coincidentally, it turns out this Alan Jeffrey papers talks about this correspondence between FRP and linear temporal logic. And then I got excited, and then I realized I needed to not do that for now. That's future work. But yeah, so that's kind of it. Thank you very much.
All right, do we have any questions?
Two questions. How does this relate to, say, the work from Walter Fontana, if you've seen that? And then the other question is, this looks very similar to operational amplifiers in electronics, and I was wondering if this is applicable. Could you actually go the other way and model op-amp circuits using this?
So to the second question, certainly. In fact, one of my collaborators is just an EE person, and the running example we have in the paper is a demodulator for a signal, just because that was the thing he pitched, and then we just built it. So the first one, I'm not aware of that work. And so I'd like to learn more about that.
Yeah, Walter Fontana has spent many, many years building like sort of a super version of this that can handle the equivalent of infinitely many ODEs.
Oh, okay. Yeah, that space, like, I approached this from like the CRN space, and my collaborators were well aware of kind of that connection there. Okay. But I'm only just baby opening my eyes to, oh my gosh, there's like this world of analog computing that we might be able to tackle here. Totally ignoring the probabilistic side that I was also jazzed about. So yeah,
worth taking a look at.
Yeah, awesome.
Yes, I was going to ask the same thing. Like, how does it compare to Kappa, which is Walter Fontana's language? And I think I can actually give you some answers already. So this is much cleaner than Kappa. So I'm glad. In fact, when I looked at Kappa, I was like, man, I wish somebody with a functional background had done this instead. Not that it's not a great language, if Walter's here. But it's kind of messy to work with. One big difference with Kappa, however, is that it reflects a lot of what happens in organic chemistry, where it's not term rewriting, it's graph rewriting. Because you actually rewrite these graphs into graphs, because that's what these molecules really look like. And then actually, some folks have done abstract interpretation on top of Kappa as well, and I suspect that work would actually port nicely to this context too. So,
okay.
I guess less of a question. I think it's fantastic work, and I think you can actually do a lot of good by cleaning up what's in Kappa and rephrasing it in this framework. So maybe the question is, if you were to extend it to something like graph rewriting instead of more of term writing, would a lot of this still work?
I am unsure. You're giving me a lot of homework to think about. I'm kind of really excited right now, because this is like a direction I just was not aware of. So, yeah. Sorry, not an answer. But no, that was really cool.
So as the biologist in the room, I'm really curious if you've been able to work with any biologists or chemists to test any of this in like actual in liquid yet, because I'm really curious if any of it would match up in the real world application.
Unfortunately not. I'm the PL person. Everyone else is a theory computation person. So we are firmly on this side of the world. I am told that I could mail order these chemicals if I wanted to, but I probably need to be trained.
No, that's fair. That's fair.
Can you suggest a resource to learning like these, families of reactions that have been, encoded in actual liquids? Like, what's the state of the art of like how complex can you actually make this work in practice today? I know that people have talked about this since I remember my PL teacher from 1997 talking about this, and it just sounded like the fantastic future that will never happen. But how far have we gotten in said time?
Specifically on the molecular programming side, a quick search for molecular program. There's a long-running NSF Expeditions grant. We're not part of that, but they've been doing excellent work across the entire spectrum of here, and they have quite a number of results, both theoretical as well as starting to realize it in actual chemistry. Still all baby steps, though, for sure.
So the key word there is molecular chemistry?
Molecular programming.
Molecular programming.
Yeah.
Okay, thank you.
Yeah, no problem.
Oh, I just want to point out that I think it is valid to have a negative molecule, and that there is going to there can either be a consumption, or if you can add stuff, you can remove it. So I don't think that's an invalid primitive to have in your language, just as a theoretical comment.
Yeah, we kind of went with these natural encodings. We could definitely, there's a lot of room. I mean, the obvious restriction here is that there's, if each data is represented by a constant number of molecules, right? Your computation can only grow so much. So there's definitely a lot of room there for trying to figure out what memory looks like and how we represent things more compactly or efficiently.
Probably just time for one more.
Have you seen cell-free TXTL systems from synthetic biology?
No.
Transcription translation systems.
That's why I'm here, I guess.
Okay,
That's great.
so the cool thing is basically you can do cellular metabolism outside of a cell, but using the chemical reactants of a cell and like adding ATP and things like that. And that's a whole area of synthetic biology. It'd be really cool if you could model those sorts of calculations or chemistry there, because it's the nice thing is because you don't have to have a living cell. You can do chemistry that would kill things otherwise, but you can actually do the chemistry of a living cell.
Yeah.
In a more controlled way.
That's a really good future direction for us to explore. I like that. Thank you. Excellent.
Okay, thank you, Peter Michael.
Thank you, everyone.